timing. So the most important thing when you take a blood gas analysis anywhere, be it PICU, outside, is how quickly your sample reaches from the patient's blood vessels to your analyzer. Now, some of the time what happens, if there's a delay, this is one of the fallacies that occur in analyzing the arterial blood gas. Remember, it's a live tissue and it keeps on metabolizing. So the longer you are going to hold the blood back before it reaches the analyzer, it is going to keep on decreasing your pH, it is going to decrease your PaO2 and going to keep on increasing the PCO2. Now the way to come out of it, in case if the analyzer is not available in ICU, it's in the lab or you're sending it outside, is to send, it is to send in the ice pack. Now remember, when we say an ice pack for an arterial blood gas analysis, there should be an ice pack which is kept below, the syringe has to be kept inside, there should be an ice pack which is kept above, and there should be a box which is closed. Most of the time I've seen, even in my unit initially, they used to take an ice pack which is kept in the refrigerator, take it out, keep a syringe on top of it. Now this ice cap bag will be very irregular. The syringe will be touching the ice bag only at 1 or 2 places, and rest of it will be exposed to the warm air outside, and this is not the way that you should take your blood for the analyzing. So it should be an ice pack which is straight. Better it should be a plastic ice pack. And nowadays you get a ready-made ice pack with a slot for the syringe where you fit it inside, put another ice pack on the top, keep it in the box and send it across. The effect of your temperature on your gases will be, in case if it is 37 degrees and above, it can keep on changing your pH to 0.01, PCO2 keeps on rising, and PO2 is going to fall down. Now the number doesn't look very alarming, but remember, in case if these are the numbers which are going to give you an OI, where you are going to think about an ECMO, you are going to think about an high frequency ventilation, it's going to make a lot of difference. And that's why in PICU these numbers are phenomenal. Now the other change which occurs is if the child is having fever or hypothermia. Now PICU, we can have either one of them. Remember, your analyzer analyzes your blood gas thinking that the child's temperature is normal. But in case the child is having a fever, it is going to change the values. And if the child is having hypothermia, either done by the doctor like we do it in the case of post-arrest, or the child is in the hypothermia just coming out of the cardiac post-cardiac surgeries, then these are the places where the hypothermia can cause a problem. And in case if the temperature is less, if you have especially kept the child on hypothermia, especially if the child is coming back from the post-cardiac surgery, then you have to subtract 5 millimeters from the PO2 that you are getting. PCO2, you have to decrease again of 2 millimeters of mercury, and you have to add 0.012 on the pH. And these are the things that you have to keep on doing at the bedside, looking at the temperature of the child. The other problem is a presence of an air bubble inside the syringe. And most of the time, what do we do when we get an air bubble? I mean, this is different. If you are having an arterial line, then you don't get an air bubble. But if you are pricking and taking the sample, what do we usually do? The nurse is going to keep on tapping on your syringe. They tap, tap, tap till the air bubble comes on the top, and they extrude out that air bubble and send rest of the sample. But we should not do that, because once the air bubble is inside and you're tapping on the needle, it's going to break into millions of small parts which might not be visible to the eye. And those parts, when they are staying back inside, they are going to change your PO2, they are going to change your pH. And remember, air bubble is full of oxygen, and there is no, if the TLC, that is the total leukocyte count in the child, is very high, and this can happen in a child with a sepsis, it can happen with a child who is having a blood cancer or ALL. When there are a lot of leukocytes, they are actively metabolizing cell, and in this case, especially if you are going to delay doing the analysis of the blood sample, this is going to make another drastic difference, just similar to what I told you initially about the the hypothermia. So it is going to bring down your pH, it is going to decrease your PO2, and it's going to falsely increase your PCO2. So the children whose leukocyte count is high, be very careful when you're analyzing. Analyze as quick as possible. In case if you are sending it to the lab, probably you have to inform the lab well in advance that we are sending the analysis, so that when the sample reaches there, it's not lying down over there, it's analyzed immediately. Now coming to the analysis of ABG, so there are 4 things that we look in the analysis: the pH, the carbon dioxide, the bicarbonate, and also the PO2. The pH, for measurement, we keep it as 7.4, although the range is 7.35 to 7.45. The PCO2, we keep the range as 40. This is for the measurement. We know the range is between 35 to 45. And bicarbonate, we keep it at the range of 24, the middle number. This is for the ease of measurement. And the most important thing is to remember about looking at the PO2. We get too carried away by looking at the acid-base analysis, and we forget that the acid-base analysis, oxygenation also is an important part. And PO2 doesn't have a number. It has to be approximately 5 times the FiO2 that we are breathing. So if we are in the room air which is not enriched, then our PO2 should be 100. But if we are breathing, say the child is breathing at 100% FiO2, then his PO2 should be around 500. So you should be looking at the FiO2 before you decide the child is having hypoxemia or not. So the 7 steps, the first step in the analysis of ABG is that always correlate your ABG with the clinical condition. ABG is just but a piece of paper if it does not correlate with your clinical condition. So if your ABG is telling something exactly opposite, don't act on it. Try to find out if this ABG is right or not before you go ahead and try to change your ventilatory settings or any other intervention. Once you have done that, then look at the pH. So as we said, the pH is going to be 7.4. So anything more than 7.4 is alkalemia or alkalosis, and less than 7.4 is acidosis. Once you have done that, then look what is causing a problem. Now there can be only 2 determinants which is going to change your pH. It is going to be the respiratory, that is your carbon dioxide. So look if your carbon dioxide is high or low, I'll be coming to that. And then look at your bicarbonate if it is high or low. So this is going to tell you if it is what process is causing this acidosis or alkalosis, and that's how we define our metabolic or respiratory causes of alkalosis and acidosis. Then how do we do it? So once we know the relationship between the pH, bicarb, and carbon dioxide, it becomes very easy. This is easy, we all know. Our bicarbonate divided by the carbon dioxide is going to give our pH relation. So in case if our bicarb goes up, this is going to cause the pH to rise up. And this is alkalosis. Because it is happening the metabolic cause, this is called as a metabolic acidosis. Similarly, if your bicarb goes down, your pH is going to decrease, and this acidosis is called as metabolic acidosis. So if you look at the relationship between your pH and bicarb, this is called as an elevator effect. If your bicarb goes up, your pH goes up. Your bicarb goes down, your pH goes down. So this is what happens in the elevator, and this is the relationship between your bicarb and the pH. And if you look at the relationship between your carbon dioxide and pH, so if your carbon dioxide goes up, your pH comes down, and this is your respiratory acidosis. If your bicarb goes down, your pH increases, and this is respiratory alkalosis. So if you look at the relationship between the respiratory causes of acidosis and alkalosis, it is called as a seesaw effect. So if your bicarb, if your carbon dioxide is going up, your pH tends to go down, and if your carbon dioxide is going down, your pH tends to go up. So it is very easy, but life is not easy. So there's a complication comes in the form of a compensation. Now our body is programmed to bring our pH back to normal because the redox potential inside the mitochondria of our cells do not work either in alkalosis and acidosis. And once your redox potential is gone off, it's knocked off, we are no longer alive. So that's why our body is programmed to bring the pH back to normal. And this programming is called as compensation. Now compensation is only to bring the pH to normal by trying to change the other part of the numerator or denominator depending on what was causing the primary event. What I mean by that is, in case my bicarb has gone up, which is caused in alkalosis, my body will compensate by increasing the carbon dioxide. Similarly, if my bicarb has gone down, my body is going to bring down my carbon dioxide. So this is a compensation, and similarly the reverse happens for the respiratory causes. The important thing to remember about the compensation is that respiratory compensation occurs very fast because we can breathe up fast or we can stop breathing very fast, but metabolic compensation takes little longer. And that's why when we talk about the compensation in metabolic causes, respiratory causes, the compensation is called as acute and chronic. So if we look at the metabolic compensation, and this metabolic compensation is done for the respiratory causes. For each 10 millimeter change in the carbon dioxide for an acute cause, in a respiratory acidosis, our bicarb changes by 1. And if it is a chronic, that it takes at least 24 to 36 hours, then our bicarb changes by 3. I will come to why there's a difference. Similarly, for alkalosis, if it is an acute alkalosis, it changes by 2, and chronic alkalosis, it changes by 3. Because your metabolic compensation is done by kidney. Now, you cannot tell your kidney immediately, if I tell my kidney, start storing bicarbonate, it doesn't do immediately. It takes some time. That's why in acute process, the compensation is slow. In chronic process, it is faster. And in case if it is a metabolic problem, the respiratory compensation is very fast, because I can start breathing faster or I can start breathing slower immediately. So the compensation is, in case there's a change in carbon dioxide, the change for carbon dioxide is expected change in carbon dioxide for bicarbonate changes 1 to 1.5 times in a case of metabolic acidosis. If it is metabolic alkalosis, then the change in carbon dioxide with the change in your bicarb is going to be 0.5 to 1. Now this change is because we can hyperventilate faster, but in case if we tell us to hypoventilate, we do it little slower. That's why the compensation for alkalosis is little less robust as compared to the compensation of the acidosis. So I'll just take another 2 minutes, sir. I'll just finish it off. So if you look at these compensation, and it's very important to look at the compensation. In PICU, these compensations are going to tell you 2 things. One, is our body compensating appropriately or not? So this gives you a function of respiratory and the kidney function indirectly. And the second, if you are looking at the compensation, is this compensation appropriate for this pH or not? If it is not, then you will know that there is an associated problem. What I mean by that is, suppose if I have an acidosis and I have a low bicarbonate. Now my carbon dioxide should go down for compensation. If I calculate how much my carbon dioxide should have gone down for this pH, and if it has not gone by that it is little higher, then I will say there is an associated respiratory problem there with this child. So a compensation adequacy tells us if a compensation is adequate or not, or if there is an ongoing secondary process which is attached to that. Now compensation looks very confusing, so we'll just recapitulate this faster before I end my talk. So if you look at the metabolic acidosis, the primary event over here is your bicarb is going down. Now to compensate for this, the event that is going to occur is that my carbon dioxide goes down. And how my carbon dioxide goes down? I hyperventilate. Now, how much my carbon dioxide should go down? My carbon dioxide will go down by 1 to 1.5 times the decrease in my bicarbonate. Now similarly, if I look at my metabolic alkalosis, the process here, primary event is that my bicarb is going up, and the compensation will be my carbon dioxide goes up. Now how much my carbon dioxide is going to go up? It is going to go up by 0.5 to 1 times the increase in my bicarb. Similarly, if you are looking at respiratory process or acidosis, I said it's an acute and chronic process. The acute is initially 12 to 24 hours because the kidney takes time to take up the bicarbonate. So the primary process here is increase in the carbon dioxide and the compensation by increasing in your bicarbonate. And how much bicarbonate is going to get accumulated? For each 10 increase in your carbon dioxide, my bicarbonate is going to increase by 1. If it is a chronic process, the primary and the compensation is same, but how much my body is going to conserve the bicarbonate. It is going to be 3 milliequivalent of bicarb for every increase in the carbon dioxide. On the contrary, if it is a respiratory alkalosis, the process is decrease in the carbon dioxide. The compensation is by decreasing the bicarbonate. And how much my bicarbonate decreases? It decreases by 2 milliequivalents for every 10 decrease in my carbon dioxide. Similarly, for the chronic process, it is the same. The compensation is going to be the 4 milliequivalents. So this is the compensation process, and this compensation process always occurs for any child who is having an acid-base analysis. I'm going to just finish my talk. Just one question from the audience, if you have understood what I've spoken now for last 15 minutes. Suppose if I have a pH of 7.10 and my bicarbonate is 14, my bicarbonate is 14 and my PCO2 is 40. What is I am having? So 7.14, is it acidic or alkalotic pH? Okay, so what is causing this acidosis? It is causing bicarbonate is low, so this bicarbonate is causing acidosis, so this is a metabolic acidosis. My PCO2 is 40. This is normal or abnormal? This is normal. So why I am not compensating? So this is an uncompensated metabolic acidosis, right? But why I am not compensating? Is something wrong with my lungs? I am supposed to hyperventilate as soon as I get this lactic acidosis. So that's where when I said the first thing, always try to correlate your ABG with your clinical sign. Now this is a child who's intubated, ventilated, he's sedated and paralyzed. So he's not going to spontaneously breathe to wash away his carbon dioxide. So don't say this is an uncompensated metabolic acidosis. The child cannot compensate because you're not letting him do it. So always remember, I'll just go to my last slide. Always remember one thing, that ABG, if it is not correlating with your clinical condition, it is but a piece of paper. Never act on that ABG if it does not correlate. ABG does not tell you the etiology, it just tells you what process is happening. And the last but not the least, the ABG does not correct, or compensation is not correcting your primary process. It is just trying to bring your pH back to normal. So it is very important to look at your ABG and decide which is a compensation and which is a primary process. Never treat your compensation. If you are going to defeat that, your body gets defeated. So the important thing to remember, as Sir said, ABG is very important. Everybody does it, but always be cautious when you are having that paper in your hand before you go and change your ventilatory settings or intervene the patients. Thank you.
Like and subscribe Eagle Media Works.